Hi everyone and welcome to the Language of Geometry review video. In this video we're going to be viewing the first part of the Language of Geometry in anticipation of our assessment. If you've already finished your interactive notebook and you got all your terms in, I would still recommend watching this video because we're going to be talking about these in a new and different order, which connects the vocab terms a lot better. And I'm going to be really emphasizing those connections that you might not have put down in your notebook. If you haven't gotten all of your notebook terms in or you want to double check to see if you're missing any, I would really recommend watching this video as well. There will be chapters listed in the YouTube description and along the YouTube timeline, and that will help you be able to keep track of what vocab terms are in the video, to be able to quickly jump to the ones you're missing and need to review on, okay? But again, I would recommend watching the whole video because I'm going to be really talking about those connections a lot more than I did before, and we're going to use new order to the things we're talking about, okay? So let's jump into things. First of all, we're going to talk about our three undefined terms, the building blocks of geometry. We call them undefined terms even though we have informal definitions for them because in mathematics, a formal definition is proving something, building it out of other things, right? So to prove something, I would build up from it from other things, okay? We're going to talk about that more in the future, but these three undefined terms are the things I have to assume. I don't get to logically build these things with other stuff. I just have to assume certain properties for them because they are what I build everything else out of, right? I got to start from something. So points, lines, and planes have that special relationship that connects them of being assumed because they're so important to build other things out of. A point is a location with no size, okay? So on this picture, we represent points with capital letters and with little circles, but points don't actually look like dots, right? They don't actually have any area or circumference or anything. I can't represent a point visually. It has no size, right? So I have to represent it with something else, in this case, a dot, right? I indicate them with letters to make them easier to reference and name, right? By saying the point C, it's a lot easier than saying the point that's the highest point or whatever. It's shorter, it's easier, and it's very clear to everyone. Points are what makes up basically everything else. Everything else is made up of points. So they're the most essential of the building blocks. Now, if points are like places on a map, then lines are kind of like roads on a map. Lines are an infinite number of points that extend infinitely far in opposite directions, right? So it's like if I made all the points on a map for every single second I was driving on a highway, I would basically be drawing a line, right? All those locations put together makes a line. Because points have no thickness, lines have no thickness, right? In the picture, it looks like this line has thickness, but it doesn't, right? It's infinitely thin. And it does not have a finite length. I can't draw infinity or an infinite length, so I have to stop at some point and put arrows to say the line keeps going. I'm just too lazy to keep drawing, okay? To name a line, I would put a double arrow over any 2 points on the line, okay? So in this case, J and I, or I and J, the order doesn't matter. You can think of it as if I was to put these 2 points on a piece of paper and draw a line that connects them and keep going forever, I've built the line JI or IJ, right? I can also name the line with a lowercase letter because I might not want to have to use 2 points to name it. I might want to go a little quicker, right? 2 points, that's a lot more words in my mouth, words on a piece of paper. 1 point, that's easier. Now, K is not a point, right? Because I can't build a line with just 1 point, but I can use just 1 letter to represent it, to go a little quicker. Points that lie on a single line are what we would call collinear points. So E and A, or A and E, right, they are collinear. They share a line. That's why it's called collinear. Co for sharing, right? Linear for line. So any 2 points that are on the same line are collinear. And in fact, even more than 2 points. If I had 5 points on a line, they'd all be collinear with each other. Now, the last of the undefined terms is what we call a plane, okay? A plane is like the map that everything else is on. It's a flat surface that goes infinitely far in all directions. So again, kind of like a point in a line, and that has no thickness. It's infinitely flat. It's two-dimensional, okay? It's thinner than a piece of paper. It's got no thickness to even be thin, right? And it goes in all directions. Again, I'm too lazy. I don't want to have to draw an infinite plane. But if I did, it would extend forever. It would go past this. This is just a representation of a plane, okay? They don't actually have edges. Now, planes, again, we name them kind of like lines with what's needed to construct them. So if I was to name this, right, if I was to try to name it with, say, D and S, well, all I've succeeded in is making a line that goes in these 2 directions. And likewise, B just keeps going in that direction, right? That's not good enough. So I can't name this with DSB, right? So to be able to say I can go in other directions, I need to pick another point. So say K. That means I could go this way or I could go this way, right? Or I could go this way, or I could go this way. And you can see this allows me to go any way I need to on this side of the line, right? This side is all covered now because I can go any amount towards K I need to, and then any amount towards D or B that I need to, right? Or away from B, away from D. And likewise, I can go away from K, right? If I know that I can go towards K, I can go away from K. And I can do that this way, I can do that this way, and so on and so forth. That allows me to build the entire plane. So I only need 3 points to build the plane, but the 3 points I pick have to be special. They have to be non-collinear, okay? So KCS is a really good choice because those 3 are non-collinear. I can construct the 3 directions I need to go in to build the plane, right? Now, I can also, again, name it with a single cursive capital letter. I can't name it with a single point like I would like to, but I can kind of do that by using just one letter. I have to assign it that letter though. Just like with a line, if it does not have a letter already named for it, I have to choose a name for it, right? I say, we could also call this plane R, right? And I get to pick the letter if I want to. But if it doesn't have a letter, I have to pick it myself. I can't just call it K or whatever. Okay. Now, points that lie on the same plane are coplanar in the same way that points that lie on the same line are collinear. This is an important distinction and important to reference because lines and points and that stuff that are on the same plane are easier to reference and connect to each other than ones that are not on the same plane, as we'll discover. They can be assumed to share some important properties. Now, let's go back and circle back to lines because lines are one of the most important building blocks in that they are really easy to build other things out of. And in fact, we might need to chop lines into some other ways to build some things. So other ways we can chop up lines, right? These ones that extend infinitely far in other directions. I could think of this as, well, what if I don't want to go infinitely in a direction? So the basic way to do that is to use a line segment, a portion of a line between 2 points on a line. Those are called the endpoints of the line. So now JI is the line segment that is stopped by the points J and I. So now these don't go infinitely far, they go finitely far. This gives them a length, and that length is what we would call distance. So the distance between 2 points is the measure or length of the line segment that connects them. If geometry is the study of space, right, where location is very important, which is why points are very important, then another thing that's very important is distance between objects, right? In geometry, I care about where things are and how far apart they are from each other. That's what where things are helps us discover, as we can see. By having points to reference, I can find the distance between those points. This is what a formal definition looks like in geometry. Notice the very specific way it is constructed out of other things, right? Distance is the measure of a line segment that connects 2 points. Line segments are the portion of a line between 2 points, right? I'm very formally building up this definition out of other blocks, right? Out of other things I have built. And those things are built out of other things, all the way down until I get to the basic building blocks of lines and points, right? So in geometry, anytime I need to reference a distance, I'm going to be using line segments. If I need to prove 2 things are the same distance apart from each other, I need to show that their line segments are of equal measure. So being comfortable with that line segment means distance, and distance is line segment. They're based on each other, built from each other, right? That is important because in the future, when you're given any math geometry problem, you're going to know, oh, I need a line segment for this, right? Or, oh, I need a distance for this. Now, line segments aren't the only things we can build with lines. We can also build rays. A ray is a different kind of subset. It's one that goes infinitely far in one direction, but not the other, right? So here, I'm starting at the point A and going infinitely towards E and past it forever, right? That's why the the ray notation looks like a lines notation, right? Like the double arrow, but I removed one of the arrows. You'll notice I also can't refer to this with 2 names like I could with line segments and lines. It didn't matter which way I ordered those, but this one it does. Because if we read left to right in geometry, so I have to start at the endpoint and then go towards the not endpoint, right? And that's where the arrow reads. It's weird because the ray starts at the endpoint, but just remember endpoints are called that because they're like bookends, right? Bookends, they're not really ends. One of them's a start, one of them's an end, right? But they're called the bookends because it's where the line ends, right? There's no line past A. That's where the line ends in that sense. So here, it's the point where it starts, right? But it is an endpoint, like a bookend. Okay, so Rays and line segments are very useful because if we're trying to build shapes, right, we're going to need line segments to build the sides of shapes. And to build shapes, we need to start with just connecting two line segments, right? To connect two line segments, or rays, is going to construct what we call an angle. These are two rays or line segments that share an endpoint. So the ray AE and the ray AF, those are my rays that go into my angle. That point A that is shared is the vertex, and the rays are the sides of the angle. Likewise, for the line segment, JI and IK, right, that is sharing the point I. So again, to construct anything in geometry, I want to use the points that I need to construct it, right? The minimum number of points needed to construct it is how I can refer to that thing, okay? Like with planes, I can name it after the three non-collinear points that construct it. With lines, the 2 points that construct it. And with angles, how many points do I need? Well, two line segments or two rays, you would need 4 points to make them unless they share a point, right? Which is why these only need 3. So notice I could say this is the angle of JI and of IK, right? But notice the I is shared, so I don't need to say I twice. I can get rid of 1, leaving me with JIK, right? That is why when I name the angle, the vertex has to go in the middle, right? Because it's kind of like I've arranged the letters in such a way that the duplicates smoosh and fuse together. You'll notice, right, I can also name these with just the vertex, A or I. Why can I do that? Because I can't construct it with just A and I, right? Well, I kind of can, okay? I kind of can, in the sense that I can refer to specifically this angle by the vertex that is unique to it. You'll notice I cannot name it with the vertex if it shares that vertex with another angle, okay? I can say the angle formed by the point, the vertex A, right? If there's only one angle that the vertex A forms. If there were 2, right, if I was to add another line like so, like this, now I can't, right, because FAM is another angle. So I can't say the vertex A. That would no longer be allowed. But if it doesn't form another angle, I can name it that. In the same way that we can also shorthand name lines with a lowercase letter and planes with a cursive letter, right, and points with a letter, I can shorthand an angle by using a number. So the angle 1 or the angle 2, right? Angles, therefore, have lots of different names, up to 4, if they don't share their vertex with anyone else, right? Pretty useful stuff. Now, in the same way that we would measure a line segment to get distance, we measure angles to get, well, angles, right, in degrees. So the measure of an angle is a degree measure that tells us essentially the amount we turn or the amount we reorient, right? So we would use this to say sweeps or turns or rotations, right? All of those are ways to use angles to describe things, just like how distance can tell us how far to go or how far apart things are, things like that, okay? Very useful building blocks, right? To be able to talk about how to turn, how far to go, and in what direction, which is what rays can tell us. Direction, distance, and turning means that we could program a robot to go anywhere in the world, right? As we're going to discover. Programming robots is a lot like building proofs in geometry, writing a set of instructions that anyone could follow to build shapes, right? So telling you where to put your pencil, the location, how far to draw it, in what direction, and then how far to turn to go in a new direction. See how you can basically build any shape by just repeating those instructions. Excellent. Now, angles are really important in geometry, and I know I'm saying that about a lot of things today, right? But there's a lot of important things. Angles are important because they form special relationships with each other to make sides, right? And angles can create very unique properties about the sides they make. So talking about angles and their relationship to each other is going to be very important for talking about those properties, which is why we have a lot of words about angles in geometry, okay? So first of all, we would learn about the different types of angles, like acute, obtuse, and right angles, okay? So in the past, we've talked about acute, obtuse, and right angles. I'm not going to review those in this video. Please look them up on your own time if you need to. They are important. You should know those definitions, okay? But we talked about those as types of angles on their own. Now we're going to study important pairs of angles, the relationships they share with each other, okay? So supplementary angles, you can see here, have a sum of their angle measures that adds up to 180 degrees, okay? This makes them the supplements of each other. In the same way that a partnership is made up of partners who are partnered with each other, supplementary angles are made up of supplements of each other that each supplement the other angle. So to add up to 180 with 130, I need a 50-degree angle, right? And then likewise, the 50-degree angle needs a 130-degree angle. So they supplement each other. Notice those two angles don't touch. They don't have to be adjacent to form the 180-degree measure. It's just the sum of their measures. Now, if I did scoot them to be adjacent to each other, right, a transformation we would call translation, as you'll discover later. If I were to move them to be next to each other, they would form that straight line, right? So supplementary angles add up to 180 degrees to form a straight line with two of their sides, right? Now, complementary angles are pretty similar sounding, but they add up to 90 degrees. So they don't form a straight line with their two sides. They form a 90-degree right angle, right? Hence why we need to remember what right angles are. Again, they don't have to be adjacent to be complements of each other. 50-degree angle is the complement of a 40-degree angle, and vice versa, even without touching, right? The important thing is the sum of their measures, that if I did make them touch, I did make them adjacent, that they would add up to 90, okay? In our notes, we went over how to better remember complementary and supplementary, okay? To me, to review it very quickly, complementary makes me think of completing, okay? That's why it's spelled with an I. It's not like giving someone a compliment. That's spelled with an I. Complementary is not spelled with an I. It's spelled with an E, right? Because it's to complete, right? To complete. In mathematics, right angles are right? That is the good angle, the correct angle, the one we are shooting for typically. So that is what completing looks like. Supplementary angles are like a supplement. They're a little extra. They're a little bonus, right? So the supplement, right, of 90 to go past that, okay, to go past it is 180 degrees. So that is what it looks like to go past 90. That's the next best angle, the next great one to work with, right? That's why it's supplementary. It's to go a little bigger. Complementary is to complete. Supplementary is to go a little bonus, right? To supplement, to go further. That's how I remember which one's the 90 and which one's the 180. And it's how I remember that the 90 degrees is what complementary is, okay? The last term I want to go over is congruency. So we've talked about a couple things now where with line segments, right? Line segments can measure distance and angles can have an angle measure, right? Both of these have a measurement attached to a geometric object. And you'll remember the notation, right? Let's review that. The notation for angles, right, is that we add this m in front of it to say that we're using a measurement. So the measure of angle 1 is 80 degrees. The measure of angle 2 is 100 degrees. And likewise, for line segments, right, I would get rid of this bar on the top that is going to appear, get rid of the bar, and now I'm talking about a number. I measure the line segment, and I get the measure ji equals 2, okay? In math, we would often use equality to say that two things are the same. But in geometry, we now have a new kind of thing to say is the same as each other, right? Which is objects. These line segments are not literally the same as each other, right? JK is a different line segment than RS. They're in different places. They're different things. But their measures are the same. They're both the same length. So in geometry, that's important. That means that some things that apply to one of them can apply to the other one, right? It's like if I know this doorway is, so wide, and all of their houses, all their doors in my house are that wide, and my couch is this wide, I can get it through each of these doorways, right? They're not literally the same doorway. I have lots of doorways to go through. It'd be nice if they were all the same door and I could just go through one door to take care of all of them. But I know that I can get through all of them because they share this important property. If I was to, on patty paper, right, draw the distance on one and overlay it on top of the other one, notice I have to rotate it and move it, right? They're not on the same location. They're not the same orientation, but their lengths are the same, okay? I would say that these line segments are congruent to each other. They share those important properties. They're not the same line segment, but they're congruent. And that's because their lengths are equal, okay? Likewise, with angles, again, the orientations are different, right? If these were line segments, their lengths would be different. Their lengths would be the same, but their orientations are different. And the pictures I've drawn to represent, right, to represent the rays, those are different. But because they don't have any lengths, all they are is an angle measure, okay? It doesn't matter how it's oriented. It doesn't matter about the length of the rays. They don't actually have a size, right? The only thing we're measuring here is the angle measure, which is the same, as we can see. This makes them congruent, right? Even though they're oriented differently and in different locations, because their angle measures are equal. So to see that as a picture, okay? On top, we have numbers. Numbers are equal to each other, okay? 2 centimeters is 2 centimeters, no matter where we find it. But the objects are different. The geometric objects are different things, different locations, different orientations. They're not literally the same object just because they share these important properties with each other. That's why it's so important to have a very clear notational difference between the length of a line segment and a line segment, okay? Notice we also use a new symbol for congruency. It looks like an equal sign, but it has this tilde above it, this squiggle, to indicate it's like equality, but it's not actually the same as equality, right? These objects are like each other, but they're not equal to each other, right? Hence the tilde, okay? To say it's kind of like that. Now, one last thing to circle back on, and this is going to be really circling back on. We're going to go back to the overview for this, okay? Now, we talked about undefined terms and building blocks of geometry, and we're talking about finding all these abstract things to represent the world around us with distances and measures of angles and directions and all that. Why do we need all this? Why do we need to overcomplicate the real world and come up with all these mathematical definitions when we could just say it's like this thing you see in the real world, right? Why is it that we have to invent math to talk about the real world? The answer is because we need inductive reasoning, okay? Inductive reasoning, if you might remember, is when you observe certain things, you have some experiences, some specific examples of things you see, and you use those to create a general principle, a conjecture that lets you make decisions. So in essence, right, math is like constructing generic versions of the things around us to prove things about those things, right? As it says here, to make generalizations about geometric figures, okay? To do that, we need to have ways to describe the geometric figures we see around us, right? And we need to have very clear definitions so it's easy to remember, okay? It's easy to understand what other people are talking about. This might not sound easy to remember right now, but think about it. Lines, line segments, and rays, you probably would have called all of those lines in everyday language, right? But they're not the same thing. They measure different things. Rays tell us direction, right? Line segments tell us distance. Those are very important differences in geometry. Why do I care about these differences, right? Think about it like you're programming a video game right now, which might sound kind of silly, but it's basically what you're doing. We're programming a set of rules to simulate the world around us, to make predictions about what might come next, right? So in essence, I'm saying, if I see this, I can predict this, right? Math is essentially the creating of those rules of prediction to say, if these two objects are the same distance apart, then the line segment between them is congruent. And that matters because so on, right? We create math to be able to predict these things in general. That way I don't have to continually reprove the same things just because this doorway is a different doorway than that doorway. I don't need to test the couch again. I know it'll work because they're the same distance apart, right? Okay, I hope that helps. I hope that helps you understand these vocab terms. I hope it helps you get a good sense of the definitions going into the assessment and in the future for review if you're checking this in the future, right? If you have any questions, please ask away in the comments. Please email me. Please let me know anywhere else or talk about it in class with me, especially during our extended Q&A sessions after our Zoom classes, okay? Other than that, I hope you have a wonderful day. And again, use those chapters, right? This video might seem kind of scary long, but you can bounce around the video as you need to and check things out as you need to, okay? See ya.